Okay, so here's the infamous, highly requested ladder problem. Let's get right to it. It says a 21.7 kilogram person climbs up a uniform ladder with negligible mass. The upper end of the ladder rests on a frictionless wall. The bottom of the ladder rests on a floor with a rough surface, where the coefficient of static friction is 0.31. The angle between the horizontal and the ladder is 60 degrees. When the person attempts to climb up the ladder, how far up the ladder will the person reach before the ladder slips? The acceleration of gravity is 9.8 meters per second squared. Okay, so I'm going to highlight important stuff, both for the given and information which will help us solve the problem. So we have a 21.7 kilogram person, that'll be the mass, and then we have a uniform ladder with negligible mass, that is very good. So with blue, I'm going to highlight information that's going to help us solve the problem. And then we have a frictionless wall, no coefficient of static friction, as you can see over here. And then we have rough surface, and then we have coefficient of static friction of 0.31. And we have the angle theta, 60 degrees. Now we have to find the distance d, as we see here in the diagram. And the first step that I suggest, let's write down the given. Let's write down what we have, and then we'll do the free body diagram. As you know, this problem is about torque, and we'll deal with torque right now. So given, we have, let's try that again, just one mass, so mass m, that is 21.7 kilograms. We have coefficient of static friction, mu sub s, 0.31, no units for that one. And then we have theta, 60 degrees. And we have acceleration due to gravity. That is from the text, meters per second squared. And from the diagram, we can see that the length of the ladder, we're going to call this length L, is 4.1 meters. So we have to find distance D, which is this over here. Okay, let's highlight that with green just so you can see. There you go. That's what we need to find. So now let's do a free body diagram. Normally I would draw the force vectors here, but then it's going to be very cluttered because we're going to have a good number of them. So let me, yeah, so I'll do it over here on this side. Whoops. Let's go for the ladder. So it's going to represent the ladder. There you go. And then let's just add a base that represents the floor, just so we can have a point of reference, okay? There you go. Now these lines that I'm drawing or I'm adding right now, they're not required or necessary. You can just do the free body diagram, but this is going to help us identify some forces. Okay, there you go. All right, so we have a force here from the wall, the normal force of the wall, right? So the ladder is resting on the wall, so we have a normal force like this. And I'm going to call that one force of the wall, FW. This is not force of weight, just force of the wall. Okay. And then we have this person standing here based on the distance d, right? This is how far up the ladder this person is standing. So more or less around here. Yeah. So we're going to add the weight vector for this person. There you go. This will be the weight vector, or mass times acceleration due to gravity. And then we have the force of friction that is keeping the wall from moving. There you go. I'm going to call this one force of friction. And we have one more. Since we have a weight here on the ladder is also resting on this floor, we need a normal force that is going against this weight. So then we'll add the force normal. So they have about the same magnitude. That's what we want. So this will be the normal force with this funny looking M. I can never get it right. So I guess I'll do it more like normalish. Not newtons, but normal force. Okay. Now, another thing I want to do is eventually we're going to need to know the x and y components for this section, like this and this. Okay? And but before we do that, let's identify where in this diagram we have torques. So we have a torque here, right? So let's say if you picture yourself pushing the ladder, well, this is the pivot, so it would go like this and it would fall. Also, as we climb up the ladder, we are exerting a torque downwards. So we're going to have a torque here on the top of the ladder and a torque here where the person is standing. And let's do that with the green. Let's see if I can do the towel. That's kind of ugly. Let's try it one more time. One more time. That's torque 1, and let's call this one torque 2. Okay. So now let's work on this one to find this distance, because we're going to need it for this torque, you'll see. Okay? So then we get blue. So it'll be this part. Let's try it again. Just draw a triangle. Now I'm going to exaggerate the size so you can see what I'm doing. I'm going to change the color of this to green so that you can see is the distance d. So this is distance d, which means, so this is theta. This is a right angle, so we have this side, it's the opposite, so it's d sine theta. And this is the adjacent side, so it's d cosine theta. Okay, you'll see why we need this, okay? You will see it. You know what, let me erase this. Just add arrows on. Okay, so now the next part, we have to sum the forces, account for all the forces present. Now the system is not moving at this point, right? So everything's in static equilibrium. So let's write it down. The system is in static equilibrium. So now let's start with the forces acting along the x direction. So sigma, forces along the x. There's no movement, so this is equal to 0, which is equal to, so forces acting along the x will be the force of the wall, normal, this one, Fw, and force of friction. So we have force of the wall minus the force of friction as their opposites. They have opposite directions. And if we consider this part, 0 equals this, then we can move force of friction to the other side and have that the force of the wall is the same as the force of friction. There you go. Now, let's do forces along the y. So for forces along the y, it's not moving, equal to 0, we have the weight and the normal force. So we have normal minus the weight of this person because they're opposite, they have opposite directions. By the same logic, we know that the normal force equals mass times acceleration due to gravity. So now, let's account for all the torques. Let's try that tau again. Now, before we do this, let me remind you what is the equation for torque with the formula, like the normal one. It's radial distance r times the force times the sine of theta. Okay, this is the general. This is the general formula for torque. So let's look at the torque on this side. So we have the force part F is the force of the wall. The distance, well, it's the distance L, 4.1. This is distance L because we have a torque applied here. And this is the pivot point, so this is distance R, or we can call it L. This is the force, and sine of theta. Okay, so it'll be, oh, it's not moving, so 0 equals distance L times the force of the wall times the sine of theta minus, now let's look at the torque here. So the force is the weight, the distance is distance, now not just distance d, but actually we're looking at this horizontal component, right? We look at the torque here, we want this is the distance we want, and we already got what this is by using trigonometry, so this is d cosine theta. Now, and you say, okay, can we include the sine of theta? Well, this is a 90-degree angle the vector makes with the horizontal, or like the floor, so we know that the sine of 90 is 1, so we don't have to include it. Then all we have to write down is radial distance, or the distance, which is d cosine theta times the force, which is mg. Now the reason why I'm not going to write sine of theta again is because this is a 90-degree angle and you're maximizing the torque. Okay, so now I'm going to rearrange this one just so it's consistent with the way we have been doing things. So force, then the length, then the sine of theta minus the force d cosine of theta. Okay, now one thing we have to remember is we know the equation for force of friction, which is coefficient of friction times the normal force. Okay, so now instead of writing force of the wall, we can write the force of friction because they're equal. So then it'll be, now I'm going to move this one to the left. That way we can have force of the wall times the length times the sine of theta is equal to this. And instead of writing force of wall, I'm going to write force of friction Oh, wait. There you go. Times the length times the sine of theta equals mass times acceleration due to gravity times distance times the cosine of theta. Instead of writing force of friction, I'm going to write coefficient of static friction times the normal. Now it's static because it's not moving, times the normal times length times sine of theta. There we go. And we also, I was going to write sine again. This is cosine. Cosine of theta. Now, we also know that the normal force is the weight. So we'll have coefficient of static friction times mg times the length times sine of theta equals mass times acceleration due to gravity times distance times cosine of theta. And we can cancel the weight on both sides. And we have coefficient of static friction times the length times the sine of theta equals distance times the cosine of theta. We're trying to find the distance. There you go. We divide by cosine of theta. And we know that sine of theta divided by cosine theta is tangent of theta. So then the distance will be coefficient of static friction times the length of the ladder times the tangent of theta. This is the equation we want. That's going to give us the distance so that everything is in static equilibrium. So now let's substitute. I was using purple. So now that we have this equation, so distance will be, let's write the equation again, just for fun. So the distance will be equal to the coefficient of static friction, that is 0.31, no units, because it is a coefficient, times the length. What was the length? 4.1 meters. Times the tangent of theta, that is 60 degrees. Let's see what that is. 0.31 times the length, 4.1, times trigonometry, tangent, 60. Class, make sure your setting is on degrees, not radians, okay? For this one, we do on degrees. Enter. 2.201 meters. Let's do 2.20 meters. That is the maximum distance so that everything remains in static equilibrium. That is, so that the ladder does not slip. There you go. That is it.